So I sent you guys a bunch of resources for stuff, and I know the people who are here are people who've been coming pretty regularly and sending me emails and stuff. So I feel like some of you might have already watched ahead and looked at those videos. But what I wanted to cover today was oxidation and reduction. So that's chapter 11 and 12, kind of mixed together. But I think, all right, wait, let me pause the recording. So, going back to what we were talking about, we're going to do oxidation and reduction. I believe there was supposed to be a little bit of stuff on your exam about oxidation, but he never really includes that. So, and it also goes along with reduction. So I'm pretty sure that's going to come back for the next exam. And it's a really big part of the material. So let's cover it in detail. So we have this, we have this, and we have this. So this is a carboxylic acid, this is an aldehyde, and what kind of alcohol is this? Primary, secondary, or tertiary? Primary. Awesome, I agree. So we have it. Calm down. Primary OH, aldehyde, and carboxylic acid. So when we draw our arrows for these kind of reactions, it's going to be like this double-sided equilibrium arrow. And we can go from the most oxygens all the way to this state. And I almost ruined the question I was going to ask you. Do we think moving to the left is oxidation, or do we think moving to the left is reduction?
Oxidation.
Oxidation, I totally agree. So I'm going to write oxidation under the left arrows, and I'm going to write reduction on the right-facing arrows. And so the sciencey definition that Dr. West tends to give you is an oxidation is any time you make more bonds to an electronegative atom. For the purposes of this class, you can just think of it as anytime you make more bonds to oxygen. So in this case, you go from one bond to two bonds, and then here you have two oxygens, so there's three bonds. And then a reduction is anytime you reduce the number of bonds to an oxygen. And if it is easier to understand, sometimes people think of it as gaining hydrogens. So this way you gain oxygens, this way you gain hydrogens. Any questions so far? Okay, cool. So I'm going to zoom in, and then at the end we will, oh, someone said one more time. Yes, so basically oxidation, we're making, here, I'll write it down in the corner. Oxidation, we make more bonds to oxygen. Whereas a reduction, we reduce the number of bonds to oxygen. Or you can say more bonds to hydrogen. Either one of those ways of thinking about it is valid. They're both going to give you the same answer. So I'm going to zoom out and write, and then I'm going to zoom in and write, and then I'll zoom back out at the end. So first we're going to go over oxidation. And when we're talking about oxidation, we go from alcohol to whatever. So for this class, the alcohol is going to be the most reduced substance that we're going to work with. So we have a primary alcohol. Sorry, I'm going to move this over just a tad. And since we have multiple reagents, I'm just going to draw the primary out twice. And then I'm also going to draw out a... What kind of alcohol is this? What do y'all think?
Which one are you pointing at? Oh, that
one. Yeah.
That one's a secondary.
Yes, I completely agree because this carbon is bonded to 2 carbons. And so I'm going to draw that out one more time. And could you chill? Thank you so much. And then the last one is tertiary. So we have 3 bonds to carbon and no hydrogen. So let's just draw that out twice. All right, so in case you want to see what I'm drawing so far, all I've done is go through and draw 2 primary, 2 secondary, and 2 tertiary alcohols. And so I'm going to zoom back in. And when we're doing oxidation, there's a whole bunch of reagents we can use, but for right now, we're going to say strong or weak. So S is strong, W is weak. So if we have a primary alcohol and we use a strong reagent, we are going to go ahead and oxidize this. So what are we going to do in an oxidation, essentially? We're making another bond to an oxygen, but how do we do that?
Is it kicking off the hydrogen and making a double bond to the oxygen?
Exactly. So someone also said moving electrons, so that's exactly what I wanted to hear. So essentially, we're going to steal this hydrogen, give these electrons back, and we end up making a double bond. So we get this. And in the actual long stepwise reaction mechanism, you would also get rid of this hydrogen, but we don't need to know every single step here. So as long as you know it goes from this to this, you're good. So if we have a strong oxidizing agent and it steals hydrogens, do you think we can do another step here, or do you think we're done? What do you guys think? We can do another step. I agree. So the strong reagent is going to take this, right? And now I'm so sorry. And now we aren't going to make a triple bond or anything. So what can we put here to oxidize the aldehyde? Hint, it was above this when we talked about it just now.
What was the question?
So if we can't make a triple bond to the oxygen, what group can we put here to oxidize the aldehyde? Yeah, we can put an oxygen. So we're going to turn this into a carboxylic acid. So if we zoom out, we can see that the primary alcohol, I'll use a different color, or I'll just use red, that's fine. So primary OH plus strong reagent turns into a carboxylic acid. And then someone asked, what does S stand for? So S is just strong reagent, and we're going to talk about what's strong and what's weak in a second. And then someone said, can you explain where you got another oxygen from? So as far as the stepwise mechanism for this goes, you really don't need to know it. It's complicated, and it's really long, so don't worry about it. What you need to know is if you have a strong reagent, you are going to take out all of these hydrogens and keep oxidizing. So if it's a primary, you take away one hydrogen, you turn it into an aldehyde, right? And then you have another hydrogen. So you take it away, and you can't go any more than a double bond. So you can't turn this into a triple bond. So the only other way to oxidize this is to turn it into a carboxylic acid and replace the hydrogen with an OH. Does that make a little bit? Okay, cool. Awesome. So let's say we have the same exact starting material, except now we're going to have a weak reagent. And I'm going to denote a weak reagent with W. So do you think the first step is going to change? Someone said yes, question mark? No, actually. So the best part about oxidations is since you don't need to know every single step, you can kind of assume that there's going to be a lot of similarities, right? So the weak reagent is going to still steal that first hydrogen and give those electrons back. So you're going to form the aldehyde. The difference is it doesn't have enough strength to come back and steal this second hydrogen. So we can say a primary OH plus a weak reagent makes an aldehyde. Also, good guess. I don't mean to be picking on you. I know it was like kind of a random question, but yeah. Does this sort of kind of make sense? Okay. So if we move on to the secondary, oh, someone said it's slowly clicking. Yay. Okay. So if we move on to the secondary alcohol, let's say we use a strong reagent at first. The strong reagent does what in the first step? It deprotonates. It steals the hydrogen. Exactly. So we make not an aldehyde, but a what? And then while you guys tell me, oh, yeah, what's up?
No, I said ketone.
Yes, you're absolutely right. So this is, oopsie, not an aldehyde anymore. It's a ketone, and we know that because there's two carbon groups. And someone asked, how do we know that this is a secondary alcohol? Because the carbon attached to the oxygen is attached to two other carbons, whereas the other one was only attached to one carbon. Okay, so the strong reagent we know can come back and steal as many hydrogens as we have, but since we don't have any hydrogens here, we are done. So we can say a secondary OH plus a plus a strong reagent is going to give you a ketone. And so what do you think the difference will be if we use a weak reagent? Aha! Someone said I thought it could do either strong or weak, and you're absolutely right. So we know that the first step is going to be the same for strong and weak. So this weak is going to steal a hydrogen and give back those electrons. And it's going to make it into a double bond, right? And it has to stop there. And since we only have one hydrogen to begin with, the strong and weak reagents are actually going to give us the same exact answer. So we get secondary OH plus weak also gives us a ketone. All right, so last but not least, tertiary alcohols. So if we have a tertiary alcohol with a strong reagent, what's the first step going to be?
Doesn't it grab the hydrogen on the alcohol, or like the alcohol attacks the strong? I don't know, something happens with the hydrogen on the alcohol, right?
Okay, why do you say the hydrogen on the alcohol?
I don't know, I was just guessing.
Well, that's a really good guess because in all the other ones, we stole a hydrogen, right? And in this one, the only hydrogen left is on the alcohol. So I definitely love your logic. The only thing here is if we stole this hydrogen, we can't make a double bond because this carbon is at capacity, right? So in reality, stealing that hydrogen won't do anything. So is there any way?
First one's no reaction, right? The tertiary ones is no reaction. Yeah, I forgot that part.
Exactly. So the tertiary alcohol in this class can never be oxidized. Because in order to do an oxidation, you need to have a hydrogen on this carbon. So to recap, primary alcohols can either turn into carboxylic acids or aldehydes, depending on whether you have a strong or a weak, reagent. And then the secondary will turn into a ketone no matter what you use. And then the tertiary cannot be oxidized no matter what you use. And then someone asked, why in all the reactions does the alcohol lose its hydrogen? So basically in the reaction, there's going to be some kind of base that's going to deprotonate the OH in order to make it more stable. Because if we kept the hydrogen on here, it would have a positive charge. So you guys don't need to know exactly what is taking the hydrogen and in what step. Just know conceptually that in order to have a neutral charge, something in the reaction had to steal this hydrogen. You're very welcome. All right.
Sorry, can you repeat that one more time?
Yeah, of course. So all you need to know in this class, conceptually, is that in order to get a neutral charge here and a happy atom, something in the reaction is going to deprotonate this alcohol.
Okay.
Make sense?
Yeah.
Okay, cool. So let's go on to our reagents. Something else he calls this is oxidizing agents. That means the same thing, so don't let that trip you up. And we are going to split up our reagents, like we said before, into strong and weak. Do y'all remember any of the reagents? We didn't cover it here, but Dr. West covered it in class. Oh, I don't know why it is being weird. Okay. And I'll give it a minute if you guys want to like look at your notes or anything. Okay, my chat disappeared. So someone brought up NaBH4, and that is a reagent we're going to talk about today, but that is actually a reducing agent. So you're getting ahead of the game. And then someone said they have to go, so have fun in your other class. This will be up later today, so you can watch it at your convenience. Okay, so someone said DMSO. That's a good one. So DMSO is going to be under the weak category. And the other weak one is PCC. 9 out of 10 times he's going to ask you about PCC, but he has brought up DMSO in the past. And as long as you guys got the weak ones, I'll tell you the strong ones because they're kind of a lot. So I'm going to zoom in. We have H2CrO4. We have Na2Cr2O7. We have oopsie, I capitalized the wrong one. KMNO4. And we also have chromium O3, and H2O. The last one he doesn't usually ever ask about, but it's in his PowerPoint, so I started including it. So everyone's question at this point is usually, do we have to memorize all of these things? Kind of, sort of, but not really. So I'm going to give you a little cheat on how to remember this. So all of these strong oxidizing agents have 4 or more oxygens. And I know you're thinking, oh, this one has 3. Well, 3 plus the 1 makes 4. So anytime this semester, if you see 4 or more oxygens, assume that it is a strong oxidizing agent. Fun fact, if you're someone who's going to take the MCAT, this is also a pretty solid tip to take with you for your MCAT studies. Any questions? I'll give you a second, and then we are going to move on to reductions. I will, before we move on, I will actually zoom out so you guys can see all of this. Okay. So let's do reductions, which are more fun to me because we actually get to do the mechanism. Students tend to hate it at first, but it's not as bad as people think it is. So we got this. Just stay with me. All right. So the first thing we are going to do is we are going to break our molecules into 2 categories. So we have aldehydes, we have ketones, we have carboxylic acids, and we have What are these called? The last one in the list. What are these guys called? Esters, exactly. So we have our aldehydes, ketones, carboxylic acids, and our esters. So we are going to talk about their order of reactivity. So I'm going to say A, B, C, and D. Which one do you guys think is the most reactive? B. Okay. A couple people said B. Why do you think B? And that doesn't necessarily mean you're right or wrong. I just love to know how you're thinking. What was the question? The question was basically, which one of these four do you think is the most reactive? And before you even answer that there might be a question you want to ask me. Like, most reactive to what? So if you're wondering what, like, someone said most reactive to what? Yeah, okay. So basically, we know that we are working with this carbon, right, to do oxidations and reductions. So something you have to think about is, what charge does the oxygen have when this electron pair goes up to the oxygen? So when we do resonance, what charge does the oxygen have? -1, exactly. So we're going to have a delta minus on the oxygen, and we're going to have a delta plus on the carbon. And that's going to be the same for all of these. So do you guys know like what a nucleophile is, what an electrophile is, or did you guys not really cover that in Orga 1? I think you kind of sort of did, right, for SN1 and SN2? Kind of? Okay, good enough. So, yeah, someone said we forgot. Yeah, no, absolutely. Everything in Orga 1 dumped out of my brain as soon as I walked out of the final, so I can imagine the same happened to you, as long as it's not the first time you're hearing those words. That's all I need. So the nucleophile is essentially what's doing the attacking, and the electrophile is what's being attacked, right? And so the nucleophile, N for nucleophile, N for negative, and the electrophile is going to be positive. So when I tell you what's the order of reactivity, I want you to tell me which of these carbons is best at being attacked, aka which one is most electrophilic, aka which one is the most positive. So with that information, which of these carbons is the most positive? Okay, so someone said they're lost, which is valid. And then someone said, don't they all have a positive center? So yes, they do. But the one thing that NMR comes back and is useful for this class is this. So do you remember when we were doing carbon NMR and we were talking about how the aldehyde has less electron density than the ketone because the ketone has 2 donating centers, whereas the aldehyde only has 1. And then we talked about how the carboxylic acid has all this resonance that goes through the carbon. You guys kind of remember talking about that? Ish? Okay, cool. It feels like there's some bells ringing now. All right, good. That's all we need. So we use that concept just to figure out how shielded or de-shielded something is. But now we can say how positive something is. So the less electron density you have, the more positive you are. So since this one has the least amount of donation, this one is the most positive. And then since this one has the most donation, this one's going to be the least positive out of these 3. So, with that being said, which one is more reactive? Is it A or is it C? Someone said wait, so I assume you have a question coming up. I shall wait. Yes, exactly. So what they said is less electron density means more reactive. In the kind of reactions we're talking about this semester, yes. So the less electron density at the electrophilic carbon, the more reactive it will be. We're going to talk about this way more in the next chapter, but I wanted to get you guys exposed to it now. So the order of reactivity, as you guys were starting to say in the chat, A is the most reactive, and then we have B, and then C and D are pretty much going to be the same, so I'm just going to say like this. Does this sort of kind of make sense so far? Okay, so someone asked, when we talk about electron density, should we consider resonance and dipole moment? Yes, that's exactly what you have to think about. So this is kind of like the dipole moment, but think of it more as electronegative effects or electronic effects. So this density is being pushed here, and we know that this resonance is being pushed across here. Okay, cool. So the reason I bring this up is because we are going to split these molecules into 2 groups. And when I split them up, this is not like something the textbook does or anything. This is just something I find to be helpful, so I passed on to you guys. So let me redraw these 4 without all the writing in it so it's not confusing. Okay, so we are going to split it up into group 1 and group 2. So we know that group 1 has the aldehydes and the ketones, and we know that this is the more reactive group. And we know that group 2 is the less reactive group. So if something is more reactive, does it need a stronger reagent, or is it okay with a weaker reagent? What do you think? Yeah, someone said weak. So the stronger you are, the weaker the reagent can be. But the weaker you are, or the less reactive you are, the stronger the reagent has to be. So this is a perfect segue to talk about the reducing agents. So just like oxidizing agents, we are going to have strong and we are going to have weak. And someone mentioned a reducing agent before. Do you want to bring it back in the mix if you still remember it? NaBH4. Okay, so NaBH4 is going to go under weak. And does anyone remember what the strong reagent is? LiAlH4, exactly. Okay, and the way I remember which one is strong and which one is weak is kind of silly, but A comes before B in the alphabet, so A is stronger than B. It might not help you at all, but remember what I said about hearing my voice just like whispering in the back of your mind while you're taking the exam? Just imagine me whispering, A comes before B, and you'll know. It'll never leave your brain. You're welcome. Okay, so we have one other reagent that is kind of going to go in the middle. So I'm going to call it a a weak strong reagent. So it's somewhere in the middle. And we call that diba. And the reason it's in between strong and weak is because it's going to only reduce group 2, but it stops at the aldehyde. That might not make sense to you right this second, but in the next 3 minutes or so, it should make more sense. So write it down for now, and then we're going to do the mechanisms, and you tell me if you're still confused. Cool? Any questions up until now? If not, here I will zoom out. Okay, so we're going to start with group 1. And yes, waiting. What's up? I assume you want me to go back here. So also, if you don't want to type your question, you can feel free to like unmute and say it, whatever makes you more comfortable. You're good? Okay. You're welcome. All right.
So, up a little bit, please.
Yes. Do you want me to go further, or is this what you wanted?
That's good. Thank you so much.
Okay. You're welcome. Okay. Just let me know when I'm good to scroll.
I'm done. Thank you.
Okay, cool. You're very welcome. So we're going to start by reducing group 1. So we are going to use first the aldehyde, and we're going to draw that out twice. Or, you know what? I won't waste that much time. I'll just do one of each. Okay, so group 1, we know is more reactive. So which reagent do we want to use? NaBH4 or LiAlH4. Okay, someone said NaBH4. And why is that? Gosh, guys, I know I haven't seen you in a bit, but no need to be shy. I don't bite. Okay, so since it's more reactive, you don't need as strong of a reagent. Exactly. And theoretically, could we use either of these reagents? Yes. But we don't need to use the super strong one because the weak one's going to react anyway. So I'll write here, can use NaBH4 or LiAlH4. You're going to get the same answers. So, just so we don't have overkill, let's say we use NaBH4. Now, the trick here, he loves to ask you a question about this. Our reducing agent is NaBH4, but we have something called the reducing species. Does anyone have any idea what the reducing species refers to? If not, that's completely okay. It's an odd one. So the reducing species. Yeah, exactly. Whatever's doing the reducing, that's head on, or whatever the expression goes. So H minus is the actual thing that's doing the reducing. So NaBH4 and LiAlH4 are the reducing agents, and the reducing species is H minus. And someone said they overthought that. You guys always do. A lot of the questions I ask are more simple than you guys think they're going to be. So, good. Just want to point that out to you guys. So, whenever I write the reaction, I am usually going to write H minus, just because I want you guys to remember that that's the reducing species. I'm going to remove the brackets just so it's easier to draw the reaction. So, we know that anything with a negative charge is a, does anyone remember from last week? A base or a nucleophile, 100%, awesome. So in this case, we don't really have a hydrogen to steal because we can't steal this one. So it's going to act like a nucleophile. It's going to come in and pow, attack right there. And if we attack here, what has to happen? Because we have technically 4 bonds, so what's going to happen? The hydrogen leaves. That's a good guess. But as far as Orgo 2 goes, we are not going to just get rid of hydrogens that are on carbons. We can get rid of hydrogens that are on heteroatoms, but if it's attached to a carbon, it's pretty solid. Solid. Someone said it's going to break a bond, so yes, you're definitely onto something. So this double bond is going to break and push those electrons up. So we're essentially doing resonance. So someone also mentioned that we're forming an anion. So exactly, we have this oxygen, we have those extra electrons now, so we end up with an anion. And we have also added an extra, we have added an extra hydrogen. Okay, so I'm going to give you guys some H2O. as your solution or your solvent. At this point, if we have a negative here, what can we do? Or I guess another way I can phrase that. Oh. Yes, so someone said it's going to form an OH. And, all right. So we have that H2O. And we said anything with a negative charge is a base or a nucleophile. So it's going to go ahead and act like a base. It's going to steal that hydrogen. And we end up with a what kind of alcohol? Primary, secondary, tertiary. Primary, super, because this carbon is only attached to one other carbon, so it's primary. Perfect. So we can say that when an aldehyde is reduced, it turns into a primary alcohol. Perfect. So now a ketone is going to be very, very, very super similar. And also, I know that it is 12:25, and I believe I finish at 12:20. I'm just going to go ahead and finish this reaction. But if anyone has to go, that's totally fine. Just pretty please do the attendance. Thank you. Okay, so we have NADH4. We're going to use that just because we can. And our reducing species is an H-, so I'm going to go ahead and just start there. So the H- is going to, bam, attack here. And the electrons from the double bond are going to do resonance and go up to the oxygen. So we end up, again, with that anion. And for bonus points, I actually don't have any authority to assign you actual extra credit or bonus points, but I mean bonus points in my heart. Does anyone know what this anion is called? It has a special name, and we covered it last chapter. The alkoxide, exactly. So anytime that O is a negative, it's going to be an alkoxide for these couple chapters. So yay, perfect. All right. So at this point, we have a negative charge, and a negative charge is going to be a what or a what? A base or a nucleophile, and in this case, you guys told me it's going to be a base, so I absolutely agree. We're going to snag a hydrogen from our solution, and we're going to make an alcohol, but now we have what kind of alcohol? Secondary, I totally agree. So a ketone, let's be consistent here, or not, I guess. A ketone will be reduced to a secondary alcohol. Ta-da! So we still have to do group 2 reductions, which we'll do next week. I am going to add an extra session for y'all next week because this whole week was a train wreck and I canceled so many things for you guys. I will send an email about that. But yeah, do you guys have any questions, comments, concerns? Do you want me to go back to anything so you can screenshot? If not, I have a little present for you guys before we go. And yes, you can absolutely take a picture Give me 1 second. He can't escape me now, because I'm at home. Okay, so Bear's going to join us for the last minute. Just tell me where you want me to scroll to, and I will go so you can take a screenshot. Bear says, thank you for the compliments. He lives for them. So someone asked, what's the electrophile again? So the electrophile is what is being attacked by the nucleophile. And we can also think of that as having a positive charge. Okay, so I will stay for an extra minute or so in case anyone has any other questions, but I'm going to stop the recording. So Bear says goodbye to everyone. Bye-bye. You're very welcome.